In this video, we take a look at implementing the A* pathfinding algorithm. So once again, let's start by checking what the exam board needed to know about the A* algorithm. Again, you need to understand the main steps and prerequisite, apply the algorithm to a data set, be able to identify it if you're shown its code, and you need to be able to read and trace it. However, as with Dijkstra's, you're not going to be required to write the code for the A* pathfinding algorithm. As the A* algorithm is a refinement of Dijkstra's shortest path, it's important you watch that video first. So the A* pathfinding algorithm is a development of Dijkstra's shortest path algorithm. Unlike Dijkstra's, A* finds the shortest path between two vertices on a weighted graph using heuristics. Known as a best first search algorithm, it performs better than Dijkstra's algorithm because not every vertex is considered. Instead, only the most optimal path is followed to the goal. With A* pathfinding, a heuristic estimates the cost of the path between the next vertex and the goal and then follows this path. It's important that the heuristic does not overestimate the cost and choose an incorrect vertex. The vertices being considered are referred to as the fringe or sometimes the frontier. The usefulness, therefore, of the A* algorithm is determined by the suitability of the heuristic. Although useful in travel routing systems, A* pathfinding is generally outperformed by other algorithms that pre-process graphs. Frequently found in video games, the algorithm is used to move non-playable characters in such a way that they appear to move intelligently. It can also be found in network packet routing, financial modelling for trading assets and goods, solving puzzles like word ladders, and social networking analysis. You'll be familiar with this illustration from the previous video. It shows towns in the county of Gloucestershire, the major road links between them, and the distance of those roads in kilometres. We also know that behind the scenes, a pathfinding algorithm only sees a set of vertices and edges for an undirected, weighted graph. The abstracted information shown here is vital, but it is not enough for the A* algorithm to work on its own. We need the addition of heuristic data, sometimes known as a best guess or educated guess. So what exactly is this additional heuristic data? Well, every time we move from one vertex to another, we also need an estimate of the remaining distance to the goal to act as our heuristic. It's important that heuristic values are sensible, and we're not simply making some sort of uninformed guess. If we seriously underestimate the remaining distance, the A* algorithm will be far less efficient. If we overestimate it, it might not work at all. Heuristics, therefore, should be what we call admissible, sensible. So we need some additional data to help us calculate these estimated heuristics. In the context of this example, calculating sensible estimates could be quite straightforward. Remember, the vertices represent physical, geographical locations on a map, and the edges represent distances in kilometres. Therefore, we could use the longitude and latitude of each vertex to calculate the straight line distance from any vertex to the destination. This process would produce an admissible heuristic as an estimate. Let's consider a different scenario. Here we have a floor plan of rooms and corridors in an adventure game. Now, while players are allowed to travel around the map freely, the game has a predetermined number of valid locations that non-player characters can stop at, represented by vertices A through N. To add a degree of artificial intelligence, NPCs should try to follow the most optimal route between any two locations. So how could we find an admissible heuristic for this scenario. We can see the map is made up of squares, so we could potentially store it as a 2D array. We could then use coordinates to specify the location of each vertex. If we were using object-oriented techniques to implement this game, then each vertex could store its own x and y coordinates. Let's say we want to estimate the remaining distance from A to L. Ignoring any obstacles such as walls, we could move 16 spaces right and 17 spaces up. So in this situation, the heuristic could be as simple as 33, 16 plus 17. This technique is known as the Manhattan approach. It gets its nickname from the streets of Manhattan in New York, which are laid out in a strict grid formation. We could make this heuristic estimate even more realistically by using Pythagoras' theorem to calculate what's known as the Euclidean distance. You can choose how to calculate the heuristic. Any reasonable best guess should work fine. Now, although the Euclidean distance might seem like the better option to use here for our heuristic, working it out will itself require more calculations than using the simple Manhattan approach. And remember, the whole point is to optimize the performance by reducing the complexity of the algorithm. Now imagine the game has portals to instantly transport you between locations or rooms with hazards that dramatically slow your progress through that section. The costs or weightings associated with the edge of the graph would now bear little relationship to the physical layout. Using the Manhattan approach as the basis for the heuristic no longer makes sense. So identifying an appropriate heuristic to use in an A-star algorithm does take some thought. Now luckily you're not expected to code the algorithm yourself. As long as you understand the importance of heuristic values, you'll be fine in the exam. So let's work through an example of the A-star pathfinding algorithm. We want to discover the shortest route from vertex, and of course we can refer to those as nodes, from A to L. As we work through the algorithm, we're going to use a table to track the data generated by the algorithm. Here we see the same table used for Dijkstra's algorithm, which lists all the vertices in the graph and some additional information, if the vertex has been visited, the distance from the start, and any previous visited vertexes. But this table is not adequate for the A-star algorithm, as we now have the additional data from the heuristic estimates to consider. This new table stores each vertex and if the vertex has been visited and the previously visited vertex. The shortest distance between each vertex and the start, which we're going to call G. The heuristic value of each vertex that we're going to call H. A final value for each vertex that we're going to call F, and this is calculated by adding together the values from G and H. Now, in reality, the heuristic for any particular vertexes can be calculated when it is required. To keep this example simple, we've pre-calculated and populated the heuristic values in advance. In a real implementation of A-star algorithm, this would obviously be inefficient. If the algorithm works well after all, many vertices may not be visited at all. So to keep the algorithm as efficient as possible, we shouldn't be carrying out needless calculations in advance if we're never going to require them. So as we're starting with vertex A, we've set its initial values. It obviously has a G value of 0, so the shortest distance from A to A is 0. And it has a heuristic of 34. Therefore its F value is 0 plus 34, G plus H. We've also set all the other G and F values to a very large number, in this case infinity. As all the other values are infinity, the value of f for the starting node actually is completely irrelevant. Some sources set it at 0, some calculate it, others ignore it. So as we now have all the data we need, we'll also remove the floor plan as we don't need it. So we begin with vertex A and consider each connected vertex that has not yet been visited. So that's C and D. Let's consider C first. We need to calculate its distance from the start, so that's its G value. So node C's G value is equal to node A's distance from the start plus the edge weight. So that's 0 plus 10. Therefore, it's going to have an F value of 10 plus its heuristic H of 22. So its F value will be 32. Now, an F value of 32 is less than infinity. So we update the table, including the previously visited vertex, to A. Okay, note that we've chosen to set all the initial shortest distances from the start and the f values to infinity. So we followed a similar process here to what we did with our Dijkstra's algorithm. You'll often find that illustrations in books and online initially have null values for G and F. And although such a level of detail is not required for A level, you need to consider this if you actually wanted to implement the algorithm. What are you going to compare your calculated values against? Okay, so let's now consider D. So that was the other vertex connected to A. Node D's G value is equal to node A's distance from the start plus the edge weight. So that's 0 plus 4. So the G value is 4. Therefore, it has an F value of 4 plus its heuristic of 27, and it equals 31. An F value of 31 is less than infinity, so we update the table, including the previously visited vertex, to A. Vertex A has now been visited, so we update the table to reflect this. We now find an unvisited vertex with the lowest F value. So currently that's D, as it has an F value of 31. D only has one vertex connected to it that hasn't already been visited, and that's E. Node E's G value is equal to node D's distance from the start plus the edge weight, so that's 4 plus 1 equals 5. Therefore, it has an F value of 5 plus its heuristic of 24 equals 29. An F value of 29 is less than infinity, so we update the table, including the previously visited vertex, which in this case now is D. Okay, vertex D has now been visited, so we update the table to reflect this. Once again, we search for an unvisited vertex with the lowest F value. So currently, that's E at 29. We then consider each vertex connected which has not been visited. So that's C, G, H and J. So you can see here we've calculated all the G and F values, and for every single one of these calculations the F value that was produced was lower than the one that already existed, which was infinity. So we update the F values and set the previous vertex as E for all of those. So we're done with vertex E, it's now been visited, so we update the table to reflect this. We search for an unvisited vertex with the lowest F value. So currently that's H with a value of 24. Now it's worth noting that if multiple vertices share the same lowest F value, we could pick any one of those possibilities, it wouldn't matter. Also notice how the algorithm is starting to stretch out in the overall direction of the destination as it identifies the next vertices to consider. These are known as the fringe or frontier. The heuristic is pulling us in the general direction of our goal. We consider each vertex connected to H that has not been visited. That's I and M. We calculate the G values and then the F values. And again, in both circumstances, we see that the calculated F value is lower than the one currently being stored. So we update the table and set the previous vertex. H has now been visited, so we update the table to reflect this. We search for an unvisited vertex with the lowest F value, and that's M with an F value of 22. Now it only has a single vertex connected to it which hasn't been visited, and that's L. Okay, so vertex L has a G value of 17 plus the edge value of 4, 21, plus the heuristic of 0, because obviously this is the goal node, so the total F value is 21. This is lower than what's in the table, so we update it. Vertex M has now been visited, so we update the table to reflect this. We have now found a route to L. It goes A, D, E, H, M, L. Now it's a common misconception that the algorithm can simply stop here. We have found a route from the start node to the goal node, but it is too early to say for sure that this is the most optimal route. There's a possibility that the route from I to L might provide a more optimal route. We need to follow the algorithm through until the goal vertex L has been visited. So we search for an unvisited vertex with the lowest F value, and currently that's L with 21. The only vertex connected to L that hasn't been visited is I. So we recalculate the F value, which is 26 this time, plus 9, and we find it's 35. Well, this F value is higher than the one we currently have stored of 29, so we don't update the table. And this reflects the fact that this is not actually a quicker, more optimal route to L than the one we already have. But of course, until we'd calculated this, we didn't know that for certain. Vertex L has now been visited, so we update the table to reflect this. At this stage, we've now found the goal vertex and we've considered all of its adjacent vertices. Once the goal is marked as visited, we can say for sure that there are no shorter paths to discover. Following the previous vertex data, we can trace a path back. L came from M, M from H, H from E, E from D, and D from A. So we now know the shortest path from A to L is A, D, E, H, M, L. So here are the steps of the A-star pathfinding algorithm presented in simple structured English. It's separated into two parts. The first, shown in yellow, calculates the shortest path from a specified start node to a goal node, and the second part, shown in red, outputs the shortest path that it's discovered. Pause the video for a moment and study the structured English in relation to the example that you've just been shown. Now, although you're not required to write the code for this algorithm, you are expected to understand and trace it. So let's take a look at some more detailed pseudocode of one possible implementation of the A-star pathfinding algorithm. If you study this pseudocode carefully, you'll be able to see a clear match from the simple structured English through to the pseudocode. Pause the video and have a look carefully at how each of the sections of structured English have made it into pseudocode, and how that relates to the logic of the worked example we just showed you. So let's consider some final thoughts on this A-star algorithm. During our example, we used a single table with a column to track which vertices had been visited. Now, in reality, you probably wouldn't store the data like this. For example, if we implemented it as an array, we wouldn't be able to mix string and integer data types easily without a lot of unnecessary casting. You could choose to implement this using two lists or dictionaries, one containing all unvisited vertices and one containing all visited vertices. Other implementations might add each vertex to a priority queue when it is first discovered. In this case, the vertex will be considered visited once it's left the queue. So having watched this video, you should be able to answer the following key questions. Can you explain the importance of heuristics in the A-star pathfinding algorithm? What do we mean by an admissible heuristic? And do you understand how the A-star pathfinding algorithm works, and can you trace its code to explain it? We know that getting to grips with data structures and all the algorithms associated with them is a very tricky area of the course, and so we've produced a book called Essential Algorithms for A-Level Computer Science that's available on Amazon. It covers all the data structures you need to know about, along with the algorithms you need to perform on them, and it covers all the exam boards. We overview each data structure, discussing its typical applications and the operations you can perform on it. We provide a QR code that jumps off to a useful page of additional resources. We then take each data structure and the algorithms you need to perform and present them first in simple structured English, then in a diagrammatic format, then in pseudocode, and finally we present you with fully coded algorithms which you need to cover on the data structures in both Python and VB, so you can actually code them up and practice them yourselves.